Continuing on to section 4.2, which is least squares regression. All right, so first thing we want to get over is what is least squares regression. So that's what we're going to figure out. We found in section 4.1 that there's a linear relation between fertility rates and life expectancy, and this was the picture we had. And I've kind of thrown in some extra bits that you're going to need later, so we'll talk about that in a minute. Now you can see when you run this with Excel, which is what this is, that Excel gives us R squared. See it right there, R squared? So how can we use that to find the correlation coefficient? Well, the correlation coefficient is R. So it's really plus or minus the square root, and you're going to have to know which one to pick. So it's either the positive square root or the negative square root. And to know this, you can either look at the slope, which in this case, the slope is negative. I don't know if you can see that. It's -5 and some change right there. Or you can look at the graph and see, oh, okay, it's got a negative slope, right? So we're actually going to want, in this case, the negative of this. And when you take the square root of 0.5803, you get about -0.7618. And there you go. So it's the plus or the minus. You'll have to judge yourself. In this case, it's the minus. Now, what kind of relationship does that appear to be? And does it appear to be linear? Using the critical value table. Okay. Well, that was back a few pages. It was right back here. So we're going to take the absolute value of RR, and then we're going to compare it to what we have available to us in this table. All right. So let me go here. Okay, so we want, for step 1, the absolute value of R. That's going to make it positive 0.7618. Right? Absolute value will turn it positive. Step 2, we need a critical value. The crit value from the table. Well, let's figure this out. N for us is 192. It says so right in the title to the graph. There were 192 countries. So N is 192. So the critical value is going to come from the table. Okay, so let me put the period in here. All right, so if I go back to the table, back a couple pages, the highest the table goes to is 30. And what I say up here is once you get a sample size larger than 30, just use 30. So use 0.361 because that's the end of the table. All right, so we're going to use 0.361. So the critical value is 0.361 for our purposes right now. And step 3, since R equals 0.7618 is greater than the crit value equal to 0.361, there appears to be a linear relation. Done. All right, a politician from an Asian country sees our data and results for life expectancy and fertility rates. She determines that to get a longer life expectancy in her country, she should just restrict the number of children to 1 per woman. What's wrong with that reasoning? Oh, so much is wrong with that reasoning. The fertility rates, let me put it this way. Since this was observational, hold on, not an experiment, we cannot argue that fertility rate causes higher life expectancy. And that's what you're doing when you make some kind of rule that says, okay, that's it, only 1 child per woman. What you're doing is making an argument that the higher fertility rate or the higher fertility rate causes lower life expectancy, or lower fertility rate will cause higher life expectancy. But that's not true. You're just observing what actually happened amongst these countries. That's not an experiment. So you can't make a cause-effect claim, right? And the reason for that is because of lurking variables, such as, what are things that might affect life expectancy and fertility rate? How about healthcare? Infrastructure, right? How many roads and power and electricity and that kind of thing. Education of the population. Education of women in particular is very important because women are the ones that have the babies, and therefore education of women affects their fertility rates greatly, etc. Alrighty. Then Suppose that a country, a 1962 country, had a fertility rate of 4.207. Using the linear equation given on the graph, what would we expect the country's life expectancy to be? Well, that'd be y hat, because this is an approximation. So we could put a little hat on its head, because it's basically saying this is the approximate. It's negative 5.0303 times 4.207 plus 82.528. And if you're wondering where I'm getting that from, let me go back. It's right up here, right? Oops, close. It's right there in the equation right there. Okay. So we'll have to go grab a calculator and type this in. All right, and when I typed it into a calculator, I got about 61.366 or so, right? There could be some rounding. You could go 61.4 or whatever. All right, so now Gabon, I should say this was life expectancy, right? So that's years. That always want to give it a unit. Gabon is a country in West Africa that actually had 4.207 children per woman and a life expectancy of 40 years. Compute, draw, and label the residual. That's what I'm doing back here. So here's Gabon, which is this red dot down here. And this distance right here is the error, how off you are. Now, every dot has its own error, right? Every single one of these dots is off a bit, right? All the ones below are off down below, and then all these ones up above are off above, right? And so we want to figure out how off is this particular country, this particular dot. Okay, so let me type that up. There we go. All right, so I take... the residual is, I should have typed this up. All right, so the residual is the observed minus the predicted. Okay, so observed minus predicted. Okay, so predicted is from the line. Observed is like actual, right? I better not put that in. That'll just confuse you. But it's the observed minus the predicted. Okay. So we observed in real life that people in Gabon were living to 40.387 years. That's observed. And then we predicted that they would live to 61.366 years right up here. That's from the line, right? That's your prediction. And then you take the difference in that, and that's negative 20.979. And that is your residual. That is literally how long this little red line is. That little red line is 20.979, and it's negative because it's below, right? All the dots down below would have negative residuals. All the dots above would have positive residuals. Every dot has a little bit of residual. Right. All right, so that residual is your error, and actually I'm going to get rid of that. There we go. All right, now what we've learned is that there's negative residuals and positive residuals, right? So the negative residual is the one we just saw. It's where the value is actually lower than what we predicted, i.e. we overestimated. Right? All right, then a positive residual would be when it's higher than we predicted, i.e. we underestimated. The estimate is always the line, because the line is where you're trying to make your predictions from. It's what you guess things are going to be. And of course, it doesn't work perfectly like that, and that's why you're off all the time a little bit. Right? And you either overestimate or underestimate. Now, there are a lot of lines that I could draw, right? When I have a scatter plot like this, you could draw lines all over the place, right? But the best line is the one that minimizes those residuals. Minimizes the residuals. Actually, it minimizes the squares of the residuals, which we'll talk about in a minute. But it minimizes the residuals, i.e. the errors for each point. In other words, the best line is off. Let me put off in quotes. By the least amount. Every line you draw is going to be off by a bit. And what you want is the one line that's off by the least amount possible. And that's the least squares regression line. Speaking of which, that's the definition, right? So the least squares regression line, also known as the line of best fit, the linear regression line, the linear model, etc. That's called the least squares regression line. Okay, so, and it's got, your y hat. It should have a y hat there. Y hat is equal to ax plus b, right? That's the line that Excel is magically finding for us on this graph. So when you do this with Excel, you just say add the trend line, it'll know, boom, there's the least squares regression line, right? So that's the regression line right there. And so what we want is we want to know what that means. Why is it doing least squares regression line? We've said we wanted to make the residuals small, but why is it the smallest square residuals? Well, that's because the sum of the residuals, look, you're going to have half of them be positive and half of them be negative, right? So the sum of just the straight residuals is going to be 0, right? So let me type that in. Hold on. There we go. So the sum of the residuals is going to be 0 every time, because the positive residuals and the negative residuals are always going to balance out and make 0, always. Will always balance out and make 0. So what we do is we square the residuals, and so that makes them all positive, because when you square a negative, it turns positive, and then you'll minimize those. And that's very similar to what we did with standard deviation. If you recall, in chapter 3, you would square the deviations and then minimize that, or deal with that in the formula. All right, so that's why. Now, one other thing to keep in mind is that we use regression models. They're a very, very powerful tool, but you don't want to go too far away from your actual data, right? So you don't want to go, let's say, for example, we have everywhere from, I don't know, about 1.6 kids per woman to about 8.3 kids per woman. So you wouldn't want to use this model, say, to make a judgment about what's a country is going to be like with 12 kids per woman, because you don't have any data out there, right? You don't want to go too far past your actual data. That would be called being outside the scope of the model. Right. Now, if I gave you a new country that was 5, you'd be like, oh, sure, and 5's right in here. Even if I had 8.5, that'd be okay, because it's real close to your data. Or 1.5, that's real close to your data. But you don't want to go too far past 8.5 and too far past 1.5, because then you're kind of getting dicey, right? The farther you go away from your actual data, the worse it gets. And that's what this is saying right here in this warning. Now, for how to make the equation, I have the calculator steps right here. And again, I cannot show it right this second, but it's on my YouTube channel right here in the calculator tutorials on youtube.com/TechieLanaJ. You want to do the 133 calculator tutorials, and it's right here. Okay. All right, let's get back to the notes. There we go. So if you watch that video, I'll show you how I come up with this equation for our infamous free lunch passing math data. This came from the calculator right here. Right there, that came from the calculator using the instructions on the previous page. All right, so let's stop right there, and I'll pick back up here with answering more questions about this data set in the next video.